shaking and stirring martinis case study, the question was whether Mr. Bond could tell the difference between martinis that were stirred and martinis that were shaken. For the sake of this example, assume he can tell the difference and is able to correctly state whether a martini had been shaken or stirred 0.75 of the time. Now suppose researcher Q does not know that Mr. Bond can tell the difference and decides to conduct an experiment to investigate. In this experiment, Mr. Bond judges 16 martinis regarding whether they were stirred or shaken. Researcher Q then does a significance test to see if Bond's performance was significantly better than the chance level of 0.50. Although we know the null hypothesis is false, experimenter Q does not. Q plans to do a one-tailed test using the 0.05 level. The power of the test is the probability the null hypothesis will be rejected. The binomial distribution for n equals 16 and pi equals 0.50 is shown here. There are 17 possible outcomes, 0 correct, 1 correct, and so on up to 16 correct. This graph shows the probability of each of the possible outcomes, assuming the probability of being correct on any given trial is 0.5. It would be unusual to get 12 or more correct if the probability of being correct on a given trial were 0.5. From the binomial distribution calculator, it can be determined that the probability of being correct on 12 or more trials is 0.038. Therefore, the null hypothesis that pi equals 0.5 can be rejected at the 0.05 level if Mr. Bond is correct on 12 or more of the trials. Since Mr. Bond has a 0.75 probability of being correct on any given trial, the binomial distribution with pi equals 0.75 gives the actual probabilities of the various outcomes. Recall that the null hypothesis that pi equals 0.5 can be rejected at the 0.05 level if Mr. Bond is correct on 12 or more of the trials. From the binomial distribution calculator, it can be determined that the probability of 12 or more correct is 0.63. This means that the probability of rejecting the null hypothesis that Mr. Bond cannot tell the difference between shaken and stirred martinis is 0.63. In other words, the power of the experiment is 0.63. In summary, the power of Q's experiment was determined by first determining how extreme the results would have to be to reject the null hypothesis, and then computing the probability of obtaining results this extreme or more extreme. In this case, the null hypothesis that Bond has no ability to distinguish shaken from stirred martinis would be rejected if he were correct 12 or more times out of 16. If he had no ability to distinguish stirred from shaken, the probability of his being correct 12 or more times is less than 0.05. However, we know that Bond has a probability of 0.75 of being correct on a given trial. This makes the probability of being correct 12 or more times equal to 0.63. In other words, the power is 0.63. Suppose a researcher were interested in whether a new method of teaching math is better than the current method. With the current method, the mean score on a math achievement test is known to be 75, with a standard deviation of 10. Assume that although the experimenter does not know it, the population mean and standard deviation for the new method are 80 and 10 respectively. The researcher plans to sample 25 subjects and do a one-tailed test of whether the population mean is significantly higher than 75. What is the probability that the researcher will correctly reject the false null hypothesis that the population mean is 75? In other words, what is the power? As in the previous example, you first determine how big the difference has to be in order to be significant. You then compute the probability of obtaining a difference that big or bigger. In order to calculate the difference needed for significance, we begin by determining the sampling distribution of the mean under the assumption that the null hypothesis is true. Recall that the null hypothesis is that the new method's mean is equal to the old method's mean of 75. Since the mean of the sampling distribution is the mean of the population, the sampling distribution of the mean has a mean of 75. Recall that the standard error of the mean is a standard deviation divided by the square root of n. Since the standard deviation is 10 and n equals 25, the standard error of the mean is 2. Here we see the results from the inverse normal calculator based on a normal distribution with a mean of 75 and a standard deviation of 2. The area above 78.29 is shaded and is equal to 5% of the total area. Therefore, to be significant at the 0.05 level, one-tailed, the sample mean must be 78.29 or higher. Now we want to find the probability of a mean above 78.29 if the population mean is not 75 as in the null hypothesis, but 80, which is the true mean for the new method. Here we see the results obtained from the normal distribution calculator. For a population with a mean of 80 and a standard deviation of 2, the probability of obtaining a value of 78.29 or higher is 0.80. This means the power is 0.80, since the null hypothesis will be correctly rejected whenever the sample mean is above 78.29. You may have noticed that these computations assume that the experimenter knew the standard deviation and therefore used a z-test. In practice, power is usually calculated assuming the experimenter will have to estimate the standard deviation and do a t-test. Procedures for calculating the power of a t-test are beyond what is covered here. Fortunately, you can use a power calculator to do the calculations for you. For this example, if the experimenter did not know that the standard deviation was 2 and planned to use a t-test, power would be 0.78, a value just below the power of 0.80 for a z-test.